All right, guys, first thing I need you to do is take out your phones and bring up on your phones your lab reports, okay, that were due yesterday. Right? I want to be able to go through that with you here, explain a few things. I need you to follow along really closely so you can kind of see where you did well, where you didn't do as well. Okay, we'll go through all of the reactions, make sure everyone understands those. Okay, we'll start off class with that. Then we're going to move on to some mole equation examples. Okay, and then working on some mole equation stuff. Probably going to be close to our last day on mole equation. We might do a little bit on Friday. We'll see. Okay. Tomorrow you will have a quiz. It's going to post at 3:20 today, as it always does, but something a little different this time. Not only am I going to include the questions, I've included a video of the solutions as well. So obviously it's not the same questions on tomorrow's quiz as it has been a couple of times. Okay, but they're very similar. So it'd be worth your while to give those questions a try, then watch the solutions video, see if you did them right, okay, because that's going to be your quiz tomorrow. Reminder also that your chemical reactions assignments are due tomorrow, but if you have it done, I'll take it early. Okay, I know I have quite a few of yours already. Okay, so totally up to you on that. Then Monday obviously is your unit exam. If you would like to take a little bit of extra time to kind of finish it up, you can write into nighttime if you want to. I think we talked about that yesterday, but that option is available as well. All right, so for the lab reports, still one big thing, and I'm seeing it often, and I want to stop seeing it is kind of the nice way to say this. In the template I gave you, I said, remember to explain your choices. I had a lot of variables that were not explained. Okay? Even though in class I said, hey guys, remember you got to identify and explain. Okay? And in your explanation you need to say the following things. Okay? I give you a pretty in-depth explanation for what I was looking for, but I still had a bunch of people that sort of manipulated the things, responding, the stuff that happens. Okay? That's not thorough enough. Okay? I need to have like very, very specific identified variables with very specific explanations. All right, so what I'm going to do is I'm going to bring up this one. Okay, so this would be an example of one that would have got 100%. Okay, so you can kind of compare it to what you wrote. Okay. So obviously the problem got to be restated in your own words in the form of a question. I wrote what determines if a reaction will occur and how will an observer know if it has occurred. Okay. For our variables, okay, in class I actually gave you a couple of them, okay, and I said the manipulated variable is the reactants for each test. They will be changed by the experimenter to observe the effects of different combinations and as subjects with different chemical properties. Okay, so in my explanation, guys, did I explain how and why they were being manipulated? I did. Okay, I said they were being manipulated by the experimenter, the different combinations, and because I needed different subjects with different chemical properties. Okay, a how and a why for each one. All right, our responding variable was the evidence or signs of a chemical change. That could be color change, temperature change, precipitates, gases evolved, okay, all of that kind of stuff. Okay, this will be different for each manipulated combination as they have different physical properties. And after each reaction, we'll also show new physical properties. Okay, so I said, here's the responding variable, how it's responding, why it's responding. Okay, we've got to have all of that in each one of our explanations. How many controlled variables are you supposed to identify? 3. Okay, I still have people only identifying 1. Okay, and the other thing I've got is people giving 1 explanation for 3 variables. Okay, that's not going to cut it for this reason. I control each of those variables differently, and part of my explanation has to be how I control them. The other part of your explanation is why I control them. That would be, how do they affect the experiment? Each one of them affects the experiment differently as well. That's why they each have to be explained separately. So, first controlled variable, temperature of the reactants. Okay? Temperature affects the rate at which compounds react, as well as other physical properties like solubility. That's the why. Okay? The how, temperature is being controlled passively, as all materials are kept at room temperature in the lab. Okay? Now I listed a few here that maybe we're not as familiar with, but I just put a few down. Atmospheric pressure. Gases are released. It's a nice spelling mistake there. Released at different rates and behave differently based on atmospheric pressure. Atmospheric pressure is being controlled passively as it will remain at whatever the surrounding air is at. Okay? Amount of reactants. Okay? The amount of reactants can influence the intensity of a reaction. The amount of reactants is being approximately controlled by using the same types of dispensers for all materials. Okay? So for each one of those, I explained how and why. And that's what I'm looking for in your reports as well. All right, in our hypothesis, what 3 words need to be in our hypothesis? If, and, then. The if part of our hypothesis is about the premise, what we think is happening. Okay? The and part describes the experiment. And the then part predicts our results or says what we'll be able to do. Okay? So I have 2 different hypotheses here. Okay? The first one is the one that's kind of more like what I said in class, and that is the if part. And in class I said, quote, Dalton's atomic theory, because he has a very good definition of what happens in a chemical change. So if a chemical reaction is the separation, joining, and or rearranging of atoms, causing new substances with new physical properties to be formed. Okay, here's the if part. That's what happens in a chemical reaction. Okay, and various ionic compounds, acids, and bases are combined on a spot plate. That's what we did in the lab. Okay, it's a very brief explanation. Okay, then temperature changes, color changes, gases evolved, and precipitates should be observed, as these are all signs that the end products are different from the reactants. Okay, that's how I would know if a chemical reaction occurred. That's what goes in the then part. Now, there's kind of differences in this between 3 out of 5, 4 out of 5, and 5 out of 5. As an example, was I very specific as to what signs I would be looking for in my hypothesis? Okay, if your hypothesis looked like this, but then the then part was, then we'll know if a reaction occurs, is that different than what I wrote? And it's less specific, and thus it's worth less marks. Okay, you have to be specific. Say these things in particular. Okay, it's about level of detail. All right, I think we'll skip the alternative hypothesis because we actually didn't do it that way. All right, then you had your prediction chart, which wasn't really important because it wasn't something I was actually going to mark. It was just for us to do before we went in there. Now, for our observations, I had a lot of people who got 2 out of 3 on the observations because they didn't follow the instructions. Okay? The instructions were, record your observations before and after. Okay? I had a lot of observations that were just turned pink, smelled bad. Okay? Like, that's the after part. How do I know if it didn't smell bad when it started if you don't say that? Okay? So before, like for example, for pair number 1, prior to mixing, both solutions were clear and odorless. Okay? Upon mixing, a strong odor and a slight drop of 3 degrees Celsius was observed. No clouding or color changes were noted. All right? Is that pretty specific? It is. Okay? For pair number 2, prior to mixing, acetic acid was a colorless solution that smelled of vinegar, while sodium hydrogen carbonate was a fine white solid. Upon mixing, a violent bubbling and fizzing ensued with a final product of a colorless solution. Okay, again, specific, and a before and an after, so there's a comparison of what occurred in the lab. Okay, everybody following what I'm looking for there? All right, for the analysis, okay, this was something that caught a few people, and I did mention this in class, words and formulae. I needed both forms for all of the reactions. I didn't always get that from everybody. So I'm just going to bring up the chart here so we can kind of walk through it together. Okay, so pair number 1, when we mixed them together, we got the odor. Okay, and we predicted that it should be a regular double replacement reaction, but that's not the way it went. So on the day of the lab, I told you one of those products, the smelly gas, was this stuff, nitrogen trihydride, or ammonia. Okay? And I told you that that N and those 3 H's came from here, so they could be eliminated. So now what's left is a reaction between sodium hydroxide and hydrogen chloride. That could be a double replacement reaction, and that would predict the other two products. Right? So if I have a double replacement reaction between those two things, H ends up with OH, and sodium ends up with chlorine. Okay. Then I have to check for any special elements. I don't have any. Drops and swaps, +1, -1, +1, -1, so those are good. And everything is balanced already, okay? Because on this side of the reaction, I had 4 hydrogens. On this side of the reaction, I have 3 + 1 is 4 hydrogens. I have 1 hydroxide, 1 hydroxide, 1 nitrogen, 1 nitrogen, 1 chlorine, 1 chlorine, 1 sodium, 1 sodium. Okay, everything was already balanced. Okay, in words, that reaction should look like this. Sodium hydroxide plus ammonium chloride arrow, and a lot of people wrote this and it was fine because I did give you that name, ammonia, okay, plus water plus sodium chloride. Okay, that's what I was looking for reaction number 1. Okay, reaction number 2 had a similar thing happen. Okay, and we said in class that this compound here is actually an ionic compound where the acetate ion, the CH3COO, is a -1 charge, and it's attached to a positively charged hydrogen. So we could really, or should really, write it this way. Okay, and it's going to have a reaction with sodium hydrogen carbonate. Now, we would have predicted a double replacement reaction that didn't occur. Okay? We had a slightly more complex replacement reaction. And I told you that because it bubbled and fizzed, the gas that was released was carbon dioxide. The carbon came from here, as did the 2 oxygens. So what was really left was a reaction between these 2 things. And now we could do a regular double replacement reaction where we predict the products. Hydrogen and sodium will switch places. Okay, so we'll have sodium acetate, which incidentally can be used to flavor salt and vinegar chips to taste like vinegar. It is a salt, after all. Okay? You'll notice they don't actually use vinegar on chips or they would be soggy. Okay? So they have a salt that tastes like it. And the other thing would be HOH. Okay? So what we'd be looking at here would be acetic acid plus sodium hydrogen carbonate gives carbon dioxide plus sodium acetate plus water. Okay, if we were writing it in words. Okay, pair number 3. This one's just a regular double replacement reaction, happens exactly as we would have learned it would in class. Okay, the metals are going to switch partners. Okay, so we are going to have sodium ending up with chlorine and magnesium ending up with hydroxide. These are both ionic compounds and they need to be dropped and swapped. That's a +1, that's a -1, so that compound is good. This is a +2 and this is a -1. Here's where people made a mistake sometimes, not everybody. When I drop and swap this, what needs to go around this? Brackets. Okay, those had to be there. Otherwise, you have 1 oxygen and 2 hydrogens, which is different than 2 hydroxides. Okay, now that we've got that, we write it in words. This would be sodium hydroxide plus magnesium chloride and it gives sodium chloride and magnesium hydroxide. Okay, this reaction produced a precipitate. That means one of the two products isn't soluble in water. If I'm really paying attention, do I need my solubility chart to figure out which one? Sodium chloride is commonly known as table salt. Can you dissolve table salt in water quite easily? So that probably wasn't the precipitate then. Okay? You could have gone to your solubility chart to figure it out for yourself for sure, which is not a bad idea. Okay? But it was the magnesium hydroxide that was the kind of gel-like precipitate that formed in that reaction. Okay? All right, pair 4 and pair 5 we didn't have to write the reactions for. Okay? Pair 6, sorry, this one's not balanced. I gotta go back and balance it. So I got 2 hydroxides on that side, so I need a 2 here. That 2 gives me 2 sodiums, so I put a 2 here. That gives me 2 chlorines. There's 2 chlorines there. Now it's balanced. So I almost forgot to balance out. Okay, for pair number 6, we've got potassium iodide. So we'll write it out in words. Okay, potassium iodide reacting with lead nitrate. But what do I need to remember about lead? It needs Roman numerals because it has more than one possible charge. If there was one thing I saw forgotten more than anything else, it would be Roman numerals in this reaction. Okay, so spoiler alert, don't forget that on the unit exam on Monday. Okay? There are some questions where that's going to play a big part. Okay? Also, don't forget it on your reactions assignment that's due tomorrow. Some of the questions need them as well. Okay, so I've got to look and figure out which one do I need, the +4 or the +2. Nitrate's always a -1, and there are 2 of them, so that gives me 2 negative charges. So that means I've got to get 2 positive charges from that lead, so it's lead 2 nitrate. Okay, it's just a double replacement reaction, so the metals just switch partners. Okay, we'll end up with potassium nitrate. And lead 2, still need the Roman numeral on this side, iodide. Now, in the lab, this was the one that turned bright yellow, made the bright yellow precipitate. All right, so I had to go to my solubility chart and figure out which one of the products wasn't soluble. Potassium nitrate is soluble, lead 2 iodide is not. So it was the lead 2 iodide that was the bright yellow solid. Okay. All right. So we got potassium is going to switch places and end up with nitrate. Lead is going to end up with iodine. We got a drop and swap. This one's a +1, that's a -1, so that compound is okay. This is a -1, that's a +2. So we got PbI2 for that. And then we need to balance the whole thing. So a 2 here will take care of my nitrates. A 2 here will take care of my potassiums and my iodines. And now it's balanced. Okay. All right, in the last pair, we had zinc reacting with hydrogen chloride. So that's going to be a single replacement reaction. Okay, zinc is a metal, so it's going to replace hydrogen, which is acting as the metal here. And we are going to end up with hydrogen by itself and zinc with chlorine. Okay, single replacement reactions have the most things to check. What thing do you suppose people forgot to check? Special elements. Hydrogen comes as a 2 when it's by itself. Okay, and this has to be dropped and swapped. Zinc is a +2, chlorine's a -1. Okay, like that. And then we've got to balance the whole thing. Putting a 2 in front of this makes that happen. All right, so we would be looking at zinc plus hydrogen chloride gives hydrogen gas, or just hydrogen, plus zinc chloride. All right, questions on that? All right, so that covers all the analysis because we covered question number 2 where you had to identify the 2 precipitates as well. Okay. All right, now for the conclusion and evaluation. So you can see there's what I did for the analysis. Now, for my conclusion, remember that you are supposed to copy and paste your hypothesis back down into the conclusion. Okay? I had a few people who just did not do that, and it does need to be there. Right? And then I have to explain why that hypothesis is acceptable or not using my data. Okay? And I had a few people like, we saw those changes, so it's good. Okay? Is that a very scientific way to accept the hypothesis? Right. So what I've got written here is first in italics, I copied and pasted my hypothesis. Okay? And then I said, upon examination of the data and observations obtained from this lab, notably the presence of color changes, evolution of gases, formation of precipitates, and temperature changes in many of the reactions, this hypothesis can be safely accepted. Because I said in my hypothesis I would see those things. Okay? This is because anytime the above indicators were present, the final products had different physical and chemical properties from their starting materials and had thus undergone a chemical reaction. Right? I said in my hypothesis that a chemical reaction is when things are separated, joined, or rearranged, and I'm confirming that the signs I saw were an indication that that happened. Okay? That's what needs to be in there. So you can see, that's like 5 lines, okay, worth of explanation. I was right is not, okay, an explanation. Does everyone follow the difference there? Again, it's level of detail. Okay, how many sources of error are you supposed to identify? 2. And in those sources of error, you're supposed to tell me how they affect the experiment and how you could prevent them, okay, or how you could fix them. So, source of error number 1, the spot plate used was clear, making it difficult to see dark colors that may have been present in the reactions. To improve on this, a white spot plate could be used, so it would be easier to see all colors of solids, not thinking except white. So, yeah. Maybe a piece of paper that you could slide underneath the watch glass periodically, they might be a better idea even than that. Okay. Second source of error, temperature in the lab did increase during the lab activity. Did anyone look at the thermometer on the wall? How many people didn't even notice there's a thermometer on the wall? Okay. There's actually a thermometer and a barometer on the wall in the chem lab because those 2 things were 2 of the control variables I listed. Okay, because they could both affect what goes on in a chemical reaction. Okay, so this was beyond the ability of the experimenter to control, and I have to say that I don't control the heat in that room. I want it to stay the same, so I didn't mess with the thermostat. Okay, the experimenter to control and could have affected the rate of reaction for some pairs. Having a room with better climate control would fix this. Your solution doesn't have to be something that you actually do, or that is not expensive. Okay? If your solution costs millions of dollars, it's still a solution. It doesn't make it any less valid. It makes it less practical, but it doesn't make it any less valid. Okay? Like when we get into biology and we're looking through the light microscopes and you say, well, it would have been nice to have an electron microscope so I could see things really, really big. Sure, it would be really nice, and that would be a way to fix it. But we don't have millions of dollars for an electron microscope. All right, is that making some sense? Are the expectations fairly clear there? Okay, so this will be the last lab for chemistry. Okay, but right away in biology, we start doing labs with microscopes and things like that. So you're going to have more lab reports coming up, okay, that will go in the same section of your marks. Okay. I would like you guys to get started on those 4, okay, because I told you I'm going to do 4 examples every day, 1 of each type of mole equation question, so here they are. All right, you guys give them a try first, and then we'll walk through them as we go here. All right, so looking at question number 1. Okay, we're looking for the number of moles, okay, so we're looking for N. They tell us the mass, 65 kilograms, and they tell us it's water, and they give it to us in word form. So we have to figure out the formula. Well, for water, you better not get that one. Okay, we should all know that one by now. Okay, so we got H2O, or HOH, doesn't matter. Okay? So to get the molar mass of H2O, I'm going to take the mass of hydrogen, multiply it by 2 because there are 2 of them, add 1 oxygen, and get 18.02 grams per mole for the molar mass of water. Now I want to calculate N. So N equals little m over big M. I know both of those numbers, so I just need to plug them in. No manipulation is necessary. Okay, 65 grams divided by 18.02 grams per mole. Okay, I had a question earlier. Mr. Coderre, will I lose marks on the exam if I don't put the units in my calculations, like here on this step? And the answer is no, you won't. Okay, your final answer absolutely must have units on it, but you don't need to include the units in your calculations. I do because I'm demonstrating and it's force of habit, and it helps me figure out what cancels and what units I get left with. But again, you don't have to put it in. All right, so when I do this operation, okay, we'll have 65 divided by 18.02, which is going to give us 3.61 moles. Okay, that is where absolutely you must have the units. Okay. All right, questions on number 1? How many people have done number 2? Okay, then we can have a look at number 2 as well. Okay, so in number 2, it's asking us what is the mass? So we're looking for little m of 8 moles. So they told us N of magnesium chloride. And again, given in words, which is how you should expect it on your unit exam on Monday. Okay, so since it's magnesium chloride, I'm going to go Mg with Cl, and because it's ionic, I'm going to drop and swap to make sure I get the right formula, and then the right molar mass. So molar mass, 24.31, that's my magnesium, plus 2 chlorines. Chlorine is 35.45, and there are 2 of them. All right, so we're looking at 95.21 grams per mole. All right, questions so far? All right, so now I've got to calculate little m. So N equals little m divided by big M. So I need to get little m, or isolate little m. Okay, so I need to move big M. Right now I'm dividing by big M. So if I want to move something, I do the opposite. So I multiply. What I do to one side, I do to the other. So now I'm looking at big M times N equals little m. So that will be 95.21 big M times 8 moles N. And that will give me my final answer. So times 8. 761.68. What are my units for that? Grams. Okay, oh, and you can see I didn't put my units in here. That should be grams per mole, and that should be moles. And then the moles will cancel, and I'd be left with grams. Okay. All right, I'll give you a few more minutes on 3 and 4. Remember, you need Avogadro's number. Okay, for 3 and 4. Whoop, too far. Okay, remember Avogadro's number. It's on your periodic table. That's it. And that's the number of particles in a mole. Okay, give you a few more minutes here, guys. Okay, sorry, guys. I'll scroll that up just a little bit so you can see it. All right, so on number 3, we're looking for the number of molecules this time. All right, which means we will need Avogadro's number. Okay, they tell us it's sodium sulfide. Okay, so that's going to help us with the molar mass. Sodium, Na plus 1, sulfide, S minus 2. So when we drop and swap, we got Na2S. So molar mass for that, that's sodium. There are 2 sodium, so I multiply it by 2, plus 1 sulfur, 32.07. All right, so we're looking at 78.05 grams per mole. Okay, now that we've got molar mass, okay, we can also write down that we know little m, 200 grams. All right, what can I calculate right now with little m and big M? N, yeah, I can calculate N right now. Okay, the formula is set up that way. So N equals little m over big M. So that's going to be 200 grams, because that's what they told me, divided by 78.05 grams per mole. Okay, the grams are going to cancel. It's going to leave me with moles. So 200 divided by, all right, so we got 2.56 moles. I'm looking for the number of molecules. Avogadro's number is the number of molecules in 1 mole, and I have 2.56 moles. So what should I do with those two numbers? Multiply them, yeah. Okay, so multiply that by 2.56, and we will get how many molecules there are in 2.56 moles. Remember, you got to bracket Avogadro's number, 6.02. Okay, use your E button, and 23. Close it off. All right, so we are looking at 1.54 times 10 to the 24 molecules. Okay, that's our final answer for that one. How many people have done number 4? I'll give you another minute on number 4, and then we'll go over that one. All right, let's look at this one. So this time we're given the number of molecules. Okay, and it's 1.2 times 10 to the 25. Is that more or less than a mole? More, yeah, a lot more. Okay. So 1.2 times 10 to the 25. We're also told that we're looking for the mass, so we're looking for little m, and they tell us that it is iron 2 nitrate. Okay, so iron, what does the Roman numeral tell me about iron? It's charged, 2 plus. Okay, and it's with nitrate, which is always a -1. What do I have to put around a polyatomic ion? All right, so there's our formula. Now we've got to get our molar mass. So iron, 55.85. There's only 1 iron, so I don't need to multiply that. How many nitrogens are there? 2. Okay, so 14.01 is nitrogen, and there are 2 of them. Okay, and how many oxygens are there? 6. So there's our oxygen times 6. All right, 179.87 grams per mole. Okay, if I want to get little m, I need n, and I can't use this formula to get it because I don't have little m. So what I have to do is I have to use Avogadro's number and the number of molecules, which is known to me because they told it to me. All right, so if I remember that Avogadro's number is the number of molecules in 1 mole, I would take the number I was given and divide it by the number of molecules in 1 mole, because this is molecules per mole. The molecules cancel and leave me with n moles. Okay? this is the same calculation you would do if I said to you, I have 36 donuts. How many dozen do I have? You'd go 36 divided by 12, right? Because there's 12 in a dozen. Same calculation. All right, when we do that, so we are going to have, I'm going to need that number later. Shoot. 1.2 E25 divided by 6.02 E23. All right, so I have 19.9 moles of this stuff. All right, now that I know what N is, now I can use the mole equation. N equals little m over big M to get little m. So I'm going to multiply both sides by big M and plug into my formula. So I'll have my 179.87 times 19.9. And obviously I'm keeping all the decimals in my calculator. Okay, so I'm taking that number there and multiplying by 179.87. Okay, so we are looking at a mass here of 3,585.45. What are my units? Grams. All right. You will have one of each of those on your unit exam on Monday. And I told you about the quiz tomorrow, right? And that the solutions are also there. Okay. There's only 3 on the quiz. So one of those 4 methods is not there, okay, on the quiz for tomorrow. All right, questions from you guys on how these work? All right, I'll give you about a 3-minute break here, and then I'm going to put some other ones on the board that I want you to try. Yes. All right, guys, I would like you to work on questions 7, 9, 10, and 11. Okay, 7, 9, 10, and 11. All right, if you finish number 11, then you can try number 13. Right? That's what we'll be working on for the remainder of classes. Those ones, the numbers in bold at the end are the answers. Now, these are worded a little bit differently. Okay, they're not as kind of simplistic as the ones we've been working on. Okay, don't let that throw you. It's just it's giving you the same information, but it's also giving you some extraneous information. That is information you do not need. Like when it's talking about reactions and stuff like that, that doesn't really matter to us as long as we know our number of moles. Like for number 7, our number of moles is 0.6. We know it's silver nitrate, so we can get molar mass. We're just looking for mass. Okay, so don't let the wording or the context of the question fool you. Right? So answers are in bold. Give those a try. Okay, I'm going to end the recording here, but that's what we're working on for the rest. Okay.